essentially, let's say this is an automaton is M. It has some set of states Q. So here it has 7 states. It has some transition function, delta, that tells it, based on a state and on an input, what state do I go to? So this is a map. It has a, or maybe I should say, yeah, delta. It has an input set sigma. We call it an input alphabet, which here is just 5, 10, and 25. And it has an initial state. Here it's the 0 state, means where you start. And it has a set of final states, F. Here, there's only one final state indicated by this double circle. Okay. So let's talk about a more interesting automaton. So just to here I have an automaton. Can everyone see this? Okay. Here I have an automaton with just 2 states. Here it has one initial state. This is its final state, and it accepts binary strings. And we want to see what binary strings do we need to input for this to accept. Like, what kind of binary strings do this accept? Anyone can just see it? Yeah.
Odd number of ones.
What's that?
Odd number of ones.
Yeah, exactly. So this automaton will accept X. So if this is M, M accepts X, if and only if X has an odd number of ones. Okay. Any questions so far? Straightforward. All right. Now let's actually get to the fun part. All right. Right now, this automaton, it can read in an input and accept and reject. But I'm going to do something more interesting. My automaton, I should remember is that word. Instead of accepting or rejecting on reading a string, it will now have an output associated with each state. So here, the output is indicated by the number after this /. So here it's 0, and here the output is 1. Okay, so now this is basically the same thing, except instead of accepting it prints a 1, and instead of rejecting it prints a 0. Okay, but here's what I'm going to do. I'm going to take this automaton and get a sequence out of it. How am I going to get a sequence out of this automaton? Well, because this accepts binary strings, what I'm going to do, I'm going to look at all natural numbers n and look at its binary representation. So 0, 1, 2, 3, 4, 5, 6. I'm going to look at natural numbers n, binary representations. And I'm going to chuck these binary representations into this automaton. So when I plug in 0 to this automaton, it just goes around this transition and gets 0. If I plug in 1, I get 1. If I plug in 1, 0, I get 1. If I plug in 1, 1, I get 0. And I keep doing this. And this, I get a sequence right here, after I do this for every natural number n. So the sequence that's obtained by this automaton by plugging in natural numbers in their binary representation, this automaton will compute the 2A Morse sequence. And like just as it was here, the nth term of the 2A Morse sequence is 1 if and only if the binary representation of n has an odd number of ones. Okay. So, and any sequence that we can obtain by making an automaton and plugging, chucking natural numbers into it, we say is automatic. So an automatic sequence is one that is obtained by running all the natural numbers in some base through the automaton. So let's look at another automatic sequence. So I can do something very, very similar, but instead of being binary, let's look at ternary.
This is a canonical way to obtain this sequence, right?
Yes. What do you mean by canonical?
You need your alphabet to be ordered in order to have a correspondence between the alphabet and the numbers 0, 1, 2, etc. length of the alphabet.
So here the alphabet of the input alphabet of this automaton would be 0, 1, being the characters on the transition. So what do you mean by alphabet?
Now that you know which, because an alphabet is, as I understand, just a finite set. Right?
Yes.
But now you know which element of this set is 0 and which is 1, and now you can take binary representations.
So there's an ordering here.
So if an alphabet was a set of 3 elements,
yes,
you'd first have to label them 0, 1, 2, and then you'd take ternary.
Yeah, that's right. Yeah. So let's do this for ternary as well. So I'll make a new automaton that will do something very, very similar, but for base 3. So just a generalization. So again, we'll have 1, 2, 3, 4, 5, 6, 7, and so forth. Maybe let's go to 8. So 0, 1. So in ternary, 0, 1, 2. Then there's no 3. So 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. And then for 9 would be 1, 0, 0, and so forth. And the automaton that I'll make will look at my number in base 3, add up all the digits, and output what is this sum of the digits mod 3. Just like, this is basically what's happening here. Here, the parity of the ones, the odd number of ones, is an equivalent way of saying, if I add up my binary representation, so 1, 1, 1, this is 3, mod 2 is 1. Yeah, okay. So let's do something very similar. So we'll have 3 states, one for each of the parities. If we see a 0, we do nothing on all of the states. If we see a 1, we increase the parity by 1. And if we see a 2, that's the same as subtracting 1. So when we see a 2, we go backwards. And notice now, our outputs, I should make them a bit bigger. Our outputs are ternary. So if we do the same thing where we pass in these ternary representations of our numbers, we'll get 0, 1, 2, 1, 2, 0, 2, 0, 1, 1, and so forth. And then this will, continuing this, will give us an infinite sequence. and this following sequence will be automatic.
So there's no notion of like output distinction, right? Like we've got different states which have the same output
Yeah.
label. Okay.
Yeah. So maybe these examples are sorry. Something. Yeah.
I think the duality from Q0 to Q2 should be the other way around.
Q0 to Q2. Oh yes, you're absolutely right. Thank you. This is 1, and this is 2. And then, did I get this? Yeah, this is right. Yeah, thank you very much. Oh wait.
No.
No.
Yeah.
So the one
Yeah.
flow was correct.
There we go. There we go. Thank you.
But outputs can be anything.
Yeah, outputs can be anything. So here I kind of picked I picked 2 examples where the inputs were the outputs. But I could make this, 7, and this could be 9, and this could be the letter B. But now, all I would change is just zeros would become 7s, 1s become 9s, and this would be Bs, right? So, but there's nothing stopping me from making my output alphabet be something completely arbitrary, or my input alphabet. You could have, as long as of a way of representing each number uniquely.
Once you do that, you're already essentially choosing.
Yeah. So yeah, I guess, but the outputs can be arbitrary. All right.
So automatic sequences always only have like a finite number of ways which like finite number of candidates for each term.
Yes. So this output alphabet here is, well, here it's like 7, 9, and beta. This is always finite. Yeah. And the input alphabet is also finite. Yeah. Okay. All right. How do I want to do this now? All right.
Sorry.
We can define another kind of automaton that will allow us to produce new automatic sequences. So let's start off with a problem. Let's say I have a set S of natural numbers n, such that n factorial can be written as a sum of 3 squares. Of integers. So x, y, z are integers. So I claim,
Natural numbers include 0?
yes, so it would be clearer to say z greater than or equal to 0. So I claim that there is an automaton such that when I feed in the binary representation of n, it will accept this binary representation of n if and only if n is in this set. So there is an automaton. So not like the one here where we have an output of 0 and 1, but the one before we have acceptance states and final states, such that there's an automaton M, such that M accepts the binary representation of n if and only if n is in S. Or in other words, if you're familiar with this language, S is regular. Which just means this. Okay. Now, how do we show this? Well, let's first look at a simpler problem. we'll look at a simpler problem and then define another structure to help us. All right, so let's look at the set S3. This set, instead of n factorial as a sum of 3 squares, let's just look at n as a sum of 3 squares. So it's going to be the same thing, but n is x squared plus y squared plus z squared, where x, y, z are integers. And I claim that this S3 is also regular. So there is some automaton, and we'll find it. And unfortunately, the automaton for S, and while this claim is true, this automaton has like 33 states, so I'm not going to draw it, but okay. But we can draw the automaton for this one. Okay. So we want to find a nice way of representing numbers that are sums of 3 squares. So this guy, Jean-Louis Legendre, mathematician, came up with a way of representing such numbers. So Legendre's 3 squared theorem says that n is in S3, or maybe it's better to say n is not in S3, if and only if the binary representation of n is of the form, or no, rather, n is equal to 4 to the power of a times 8b plus 7 for non-negative integers a and b. How did he show that? The proof is very long. We're going to take this as a black box. So every number that is not a sum of 3 squares has this very nice form. Okay. And what we're going to do is take this nice form and see how it looks in binary. So we want to look at these binary representations of numbers of this form. So 4 to the a. Right away, when we multiply 4 to the a by anything, we'll get an even number of zeros in the binary representation. It could be like no zeros at all, but 0 is even. And then 8b plus 7 will give us 1, 1, 1. And then what's before that doesn't really matter. This would be a binary representation of b. There's something there. So how we get this is we have some number b. It has some binary representation. We don't really care about what it is. We multiply it by 8, which will give us just whatever b is, then 0, 0, 0 after it. Then add 7 to it, which will change those last 3 zeros to 3 ones. And then multiply by 4 to the a, which will give us an even number of zeros. And now, once we've expressed this number in this form, it's actually quite straightforward to create an automaton that will accept it. Oh man. Yeah, I'm going a bit slow. We might not get to that.
We need to go to 6:30.
All right. So what our automaton is going to do is basically, we can imagine its thought process as follows. It will read, whatever, but we only only cares about what it sees at the very end, right? The dot 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 is not important, but once it sees 1 1 1 followed by an even number of zeros, then it knows, all right, we're in. So if it sees 1 1 1,
Are we really trying to back or back?
what's that?
Are we really least significant to most significant or most significant?
Yeah, that's a good question. We're reading most significant digits, so even though you're right, it would be easier to do least significant. Like we instead we could. So Shaul was suggesting that instead of reading the binary representation left to right, we could read it right to left, and then we could just see does it start with an even number of zeros, and then have 1 1 1, and then the end doesn't matter.
We can do this.
We
can
can.
make an automaton start reading things in the opposite direction.
So yeah, so we could do that, and then we would have to reverse the automaton, meaning that it would accept inputs if and only if the reverse of that input is accepted by this other automaton.
Consider it like exchange the initial and final states, and you have a non-deterministic one, and then determinize it.
Yeah, so there are ways of doing this, but we're going to stick with most significant. Yeah. Did you have a question?
Not really, but if you do like the left, wouldn't you need the entire input to start with?
Sorry, could you repeat that?
If you're going to do like the left, wouldn't you need the entire input string to start with?
Right. So we are going to be reading the entire input, but the nice thing about this is we only need to determine whether or not the binary representation of n is of this form. We only need very little amount of memory. We've seen 3 ones, and then we just need the parity of the zeros that follow. So it's 3 ones followed by even or odd.
I think I think the question was, wouldn't we need to know the entire binary representation at the beginning? And I don't think that's true.
Oh.
Like automata can only process 1 bit at a time.
Right. Yeah. So it would, let's say our number is, let me come up with an example here. Let's say we have I don't know what number this corresponds to. But say this is my binary representation. This is of this form. But and this would be my number b. So here would be 2. And what my automaton will do once I've drawn it is it will read the 1, then the 0, then the 1, then the 1, then the 1, then the 0, 0, 0, 0.
No, I meant if you're going to read it from right to left,
Yes.
in order, you need somebody to flip the input. Wouldn't that need you to read the entire input at least once?
Okay, yeah, so, sorry, again, now, okay, yeah, I understand your question. All right, so you can make an automaton. So if I have an automaton that accepts x, then I can make another automaton that will accept the reverse of x, if and only if this first automaton accepts x. So there are ways of doing this that don't require knowing all of x beforehand. But that's outside of the scope for this talk. Yeah. As in, I don't remember. Okay. All right. Let's finish this up. Okay. So we want to see 3 ones and then an even number of zeros. So we'll see we have an odd number of zeros, and then no. Yeah. Okay. It's like this, and then I think we're. Is that sufficient? I'm missing.
Restarts.
Yeah. So I haven't done that quite yet. Just. Yeah. Okay. So if the string is empty, we don't want to accept because we need the 3 ones.
This isn't correct.
Oh, we're not done yet.
What if a is 0?
What if?
Like a is.
So I haven't defined fully. There's other transitions that I haven't drawn.
No.
Yeah.
You should erase the last because indeed, if our number is 7, then we're not going to end at the final number.
Yeah, we're going to have multiple final states.
Well, we can.
So, yeah, my bad, I should have emphasized this. Our automaton can have, this could be a final state, this could be a final state. As long as it ends on one final state, we're good. So yeah, that was on my bad, should have emphasized that. So, if we see 7, we accept. And then if we see an even number of zeros, so 0, 0, we should also accept.
You don't need that state.
Yeah.
Second thing.
Oh yeah, you're right, I actually don't need this state.
We can just go
Yeah,
back.
we could just do this. That's what I was doing initially, yeah. Like that. Yeah. And then, if I'm in the process of reading my 1s and then a 0 interrupts me, I'll have to go all the way back to the end. Oh yeah, so, yeah, that's right. And then if a 0 interrupts me here, I'll have to go back to the end. And then if I see a 0 here, I don't care. And if I'm reading my 1s, oh yeah, so here is why we needed it.
Oh, yeah.
If I do this, there's a problem. Because then the string 1, 1, 1, 0, 0, 1 will be accepted. So it's sneaky, it gets you. Yeah. So we do need that extra state, yeah. So I was a bit hesitant at first too. Like that. Okay. And then if it's an even number of zeros, it accepts. Like that. And then here, if I see a 1, I'm okay. Because I could have 4 1s in a row, nothing's stopping me. And then here, if I see a 1, I go here. Because instead of starting from the end, I've seen 1 and then same thing.
I wonder if ATAL improves it.
I don't remember how to prove these things anymore. All right. Okay, so here is our automaton that will accept n if and only if it is not a sum of 3 squares. Because it's not an S3. So how do we make it accept sums of 3 squares? Easy. Every number that's not accepted is now accepted. Every number that's accepted is no longer accepted. So every final state becomes not final, and every not final state becomes final. And this will accept S3. Because I'm out of time, thank you very much. Unfortunately, I didn't get a chance to actually talk about that or even apply automatic sequences to this, but maybe for next time. Yeah, for next. All right. Are there any questions? Yeah?
Are there any results for recognizing automatic sequences? Are there results about classifying automatic sequences?
So that's so what do you mean by classifying?
As in, if you're given a sequence, could you say if there's a finite automata that produces this sequence?
Right. I don't know of any.
Like the nth term, for example, of the sequence is generated. There's a finite automata such that for any value of n, the nth
So I don't know of any general way.
Like each element is from a finite set, for example.
But it's not like it's if you're given a sequence, you have a C. The only thing given is you're essentially given a form. So you're given which generally would suggest that it's.
So I don't know of a way to take an infinite sequence and here's an automaton for it. You could guess the sequence, guess the automaton, but then it's an infinite sequence. So if you have some way of characterizing the nth term, then maybe you can show that there is an automaton that will compute this function that finds the nth term. Yeah.
Is it true that a sequence is automatic if and only if it's regular?
So an automatic sequence could have outputs that are not 0 or 1, right?
Yeah.
So saying a regular sequence isn't very, there's no notion of regularity for sequences, but I understand what your question is.
Because it's not, I guess it's not
Yeah.
finite, right?
So here's something you could do that might answer your question partially. I will erase. I'll erase this. If I have, let's take the sequence I had from before that will like compute the running sum mod 3 of my ternary representation. The automaton I had from before. So this would be an output of 0, 1, 2, 1, 2, 1, 2, and then I have to not mess this one up again. 2, 1, yeah. Then the sequence I get here, okay, I have to like, you know, draw the thing again. But again, I give me like 1, 2, whatever. I'm just making numbers up. But what I can do is say, I want an automaton that will accept a number n if the nth term of this sequence is 2. So maybe I want an automaton that will accept if the nth term of this sequence is like 2 or 1. So how would I do that? Well, I have this automaton here. I have the outputs 2. I'm just gonna make this a final state and make these ones not final. So it's very easy, right? Similarly, you know, so it's quite simple to go from, you know, switch between them.
Can you say make a sequence that accepts a number if only with the prefix of this automatic?
Could you repeat that? If the
It's a
prefix,
prefix of the automatic sequence.
if the prefix,
If it's a prefix of it.
oh, if it's a prefix, if it accepts, it accepts, what is a prefix?
It accepts a number if its ternary representation is the first n. If it's the cutoff at some point of the sequence. It would accept in this case 0, 1, 0, 0, 1, 0, 1, 2, 1, 2, 1, etc.
Oh, you mean like it would accept all numbers here? And you just say it accepts numbers that are less than something.
No, not less than. It accepts numbers which are a prefix of the sequence. The number that equals the first element of the sequence. Number that's equal to the. It would accept the string 0. It would accept the string 0, 1. It would accept the string 0, 1, 2. It would accept
Oh,
the string 0, 1,
I see
2,
what you
1.
mean. I see what you mean.
So the sequence is fixed, and then you're trying to build.
Yeah, so you're fixed a sequence, and then now you're using it as an input, and trying to match.
Well, have you fixed you haven't fixed an index before.
No, you're saying you have a sequence. You consider the set of all prefixes in the sequence.
Right. That's a finite, those are finite strings.
Yes.
Right.
The first k element.
I think yes. Why do I think? Whoops. Okay. Why do I think the answer is yes? So here's what I think.
I think you're right that it's yes.
You can. It's like the same argument as like, you know, a union of regular languages is regular. You simulate 2 automata at the same time. You simulate. Oh wait, no.
Union, right?
Wait, you're reading this as an input. I'm not sure. I'm not thinking about that.
If the sequence is similar to a Hierarchical number, it might be impossible.
Yeah, because you don't even know, like, if you know what the sequence that generates this, if you know the automaton that generates this, yeah, I'm not sure. I'm not thinking about that. Yeah, that's interesting. Right. There was another thing I wanted to define, which was, just none of you are leaving, so I'll hold you hostage. That was like, the talk is done, so you can leave if you'd like.
To go in like 15 minutes.
Okay, so I'll just keep talking for another 15 minutes. So the way that I erased it, but we had this n factorial is a sum of 3 squares that I never got to. And to do that, let's look at n factorial, how we can recognize whether n factorial is a sum of 3 squares. Okay, I didn't erase that word. So what we're going to do, every number n can be decomposed into its odd part, we'll say, and multiplied by the highest power of 2 that divides it. So for example, 40 is 5 times 8. So here g of 40 would be 5, and nu sub 2 of 40 would be 8. So for every number, we just divide by the highest power of 2 that divides it, and then we get an odd number. Hmm? Oh yes, thank you very much. This is 3, yeah. So nu sub 2 of 40 is 3. Okay. And if I take a product of 2 numbers, so let's say I have n times m, and what would the odd part of n times m be? Well, you know,
Product of.
yeah, exactly. Well, yeah, it's just the product here. There's no well, it's the product. How about nu sub 2 of the product? Exactly, the sum. So now, what is g of n factorial? And what is nu 2 of n factorial? This is the running product from 1 to n of g of I. I'll drop my parentheses a little lower. Use 2 of n factorial is this running sum from 1 to n. And remember, we had this Legendre's 3 square theorem that said that n was in S3 if and only if, or was not in S3 if and only if n was of the form 4 to the a times a to b plus 7. So how can we relate, this form to these nu 2 and g? Well, this would be my nu 2, where my nu 2 comes from. So I want nu 2 of n to be even. So this is if and only if nu 2 of n is even, so 0, 1, 2, and g of n is 7 mod 8.
You mean n factorial?
Huh?
You mean n factorial?
So right now I'm looking at n. But yeah, now, how about n factorial? Well, I still want to write it in this form, but now, instead of looking at just nu 2 of n, or factorial, I now want this running sum to be 0 mod 2, and I now want this running product to be 7 mod 8. Okay. So I want a way of, and I'm going to claim this, or assert this rather. I can find automata, or the sequence. How do I want to phrase this? The sequence nu 2 of 0, nu 2 of 1, nu 2 of 2, nu 2 of n is automatic. The automaton for that is actually quite simple. We just want to, see if it has an even number of zeros at the end. So it's like basically the same thing we did here. And so is the sequence g of 0, g of 1, g of 2, up to, you know, forever. Except that sequence, g of 0, g of 1, and so forth, the outputs of it, we want it to be mod 8. So we're gonna, so g of 0 mod 8, g of 1 mod 8. The outputs of it are going to be 0 through 7. And the automaton for this is actually quite messy, so I'm not going to draw that.
Oh, yeah.
But you're just going to be doing, you're just going to be looking at, oh no, it's not messy. You just look at the last 3 characters before zeros at the end of your string. So you want 1, 1, 1, and then before the zeros. Yeah, so this is actually fine. Okay, but now what you want is, I have this sequence, and I want to take a running sum of the elements of this sequence. And I want this running sum to correspond to an automaton. So I can decide whether or not this running sum is like 0 mod 2. And I want this running product of this sequence to also correspond to an automaton. And I want to see if that automaton has the running product 7 mod 8. So I can briefly introduce this in the next 5 minutes. So to do this running sum and running product, we need a new piece of machinery called the transducer. And the transducer, what it does is it's an automaton, but instead of outputting, you know, a character, some character, it outputs a new sequence. So let's say I have, you know, let's say I have my 2 or more sequence from all the way back. And I want to take the running sum of this sequence. So what is the running sum of this sequence? I'll just call it T of T. The running sum is, you know, I add, you know, I take a running sum. So 0, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 0. It keeps on going. So, you know, at a certain point, the nth term is the sum of the first n terms of the 2 or more sequence. Okay, and I claim that this running sum sequence is automatic. So there's some automaton that will, you know, given n, take the binary representation of n, chuck it in, and give me, say, this term. Okay. So to do this,
For
Yeah.
all possible t's, it's impossible because.
so not for every t. So if my initial sequence is automatic, so yeah, I should have this way. So rather, if I have an automatic sequence, you know, like this, and I take its running sum or a similar operation, then the resulting sequence is still automatic. So it's closed under so-called transduction, which I'll define now. So a transducer, like I said, is an automaton that outputs a sequence. In this case, we're going to have it output this running sum. And for it to do that, instead of having outputs on the states, it's going to have outputs on the edges. This. Yeah, so each edge now has an output associated with it. So this would be the character I need to read to take this transition, and this would be the output. So this transducer, this is called a transducer. It's going to read in the sequence character by character. So first it reads a 0, we have an output of 0. Then it reads a 1, and it goes here, has an output of 1. Then it sees another 1, it goes back, and has a 0. And it keeps on doing this, where it so this transducer reads in an infinite sequence and produces this new infinite sequence, which is the running sum.
So it's not an automata because
So yeah, this is not
finite automata.
yeah, this is a new piece of machinery. So it's like very similar to an automaton, but it's not the same thing.
Because it has an infinite number of outputs.
Exactly. Its outputs are now sequences. Yeah. So with this transducer, where do I write? I can write it here. So there's a theorem, again, a black box theorem. That states that if I have an automatic sequence, so this is a guy named Michel Decking who wrote this in 1994. We'll use it as a black box. If I have an automatic sequence and I have a transducer, and I transduce this automatic sequence, I will get another automatic sequence.
How fast is the proof?
It's like 3 pages long and it's extremely messy. The proof of this is, so like, it's very similar to pumping lemma, where you like find some repetition and then this repetition implies that the number of states visited is like, the number of paths you can take is finite. Finite means there's a state for each of those paths. It's a very messy proof. It would take me hours to even understand what's going on. Okay, so the point is that we can now take running sums, and there's still some automaton. I think it has like 8 states or something. Whatever. Such that when I input, you know, n in binary, it'll give me 0 here. Okay. This automaton exists. It has 8 states, and as you take more and more running sums, you get like the states explode. Okay, but the point is now there is an automaton that will take n and give me this running sum of nu2 mod n. Sorry, this should be I. This should be I. It will take this running sum of nu2. And there's another automaton that will take a running product. So there's another transducer that will take a running product mod 7 and just does like multiplication mod 8 and gives me the last 3 digits. Or the mod 8. There's a transducer that does a running product, and if you apply it to this automaton that finds the G, there's an automaton that now spits what this is. This is mod 8. And then, by like, you know, taking the and, I can now find an automaton that will tell me if n factorial is or is not a sum of 3 squares. And this automaton, I'll show it to you. It has like 30 something states. It's very ugly. I'm not going to draw it, I just want to see if I can find it. But yeah. So with these transducers, yeah, I'll show it later. But with these transducers, we can now form new sequences to do more interesting things. Again, interest is subjective. And to answer more complicated problems. Yeah. All right. So that's like the end of my talk. Well, okay. Now, are there any questions?
Wait, you were